Welcome back to the channel, everybody. Today I'm doing a short video about how to measure internal resistance of a battery. And the reason I'm doing this is I was recently out taking pictures with my Canon camera, and it was in the car all night, and the cold, the camera kept freezing up. So I assumed the battery, being a little older, or third-party cameras, also with a newer, larger lens, maybe it was having trouble supplying the energy that the camera needed. Looking around, I didn't find much in the way of actual technical data on any of Canon's batteries, so I decided to measure some of my own performance characteristics. And I have some third-party batteries, some older batteries, etc., to see how things look. So I'm not comparing batteries to like whose brand is better, but I just wanted to get some key characteristics. Which, when you're talking about batteries, people care about really two things. The biggest thing you'll see is capacity. So that's measured in milliamp hours. So this one's 18650. Well, 1865. That means it'll put out about 2 amps for an hour before that battery is completely dead. The other item that you will never see printed on a battery, but it's important to engineers, is what is the internal resistance of that battery. Essentially, every battery is like a perfect voltage source with a resistor in series before that voltage or that current can leave the battery. And what that does is it limits the amount of maximum power that that battery can put out. And it's typically also temperature sensitive. As batteries get colder, that internal resistance goes up and they're able to deliver less power. That's why if you try and start your car in cold winter, it starts hard. That's why when batteries, like your phone, is cold, it seems to die very quickly. It's because internally that battery is dissipating that energy instead of actually getting it out to your load, which would be your car, your phone, etc. So what I have here is a fairly crude setup, but measuring this type of parameter is not something you need a complex lab setup for in most cases, especially if you're just trying to get good enough. If you have 2 multimeters and some high power resistors, you can get a fairly accurate within 1% measurement value. And there's 2 keys to do that. Step 1 is you want to have what's called a Kelvin connection. So on these connect to my battery here. And actually the way I made these battery connectors, just to jump into that, if we zoom back in again, I actually just took a piece of copper tape, folded it over on itself, and then soldered a piece of wire onto it. And that tends to fit perfectly into the battery terminals. It's about the same thickness as what the copper plates in the charger are. So I said good enough for that. These molded batteries, that can be one of the challenges, how to make good connection to those terminals. Like I was saying, Kelvin connections. So what does that mean? You can see the diagram in the corner, but essentially you have 2 sets of cables connected to whatever it is you're measuring. And this isn't a lab how you measure precise resistance, voltage, currents, etc. So to each one of my battery terminals, I have 2 wires connected. One set of wires goes to a voltage meter, and this is just a cheap DMM. The other set of wires goes through a current loop, through this current meter, through my power resistors here and back to the battery. And let me draw that out for you guys. So drawing out what that is, I'm going to make our little battery right here, and let's just put some dotted lines. So this is our battery. What your battery is a perfect voltage source, and then it has a internal resistance. We'll call that R internal. Then that battery leaves. This is the plus terminal. This is the minus terminal. So right here, we're going to go out. We're going to go through a current meter. So this is going to measure current. We're going to go through our load. And then we're going to go back to the battery. Change colors here. We have our voltmeter, just a DMM, and I'm going to connect terminals as close to the battery as possible to that guy. What this allows us to do is measure the voltage right at the battery terminal and ignore any loss in these random stray wires, additional resistance in the amp meter. We'll also call this a DMM. Current, voltage. Boom. So that gives us a perfect measurement of the voltage right at this battery terminal. Then this meter, being a series loop, measures the current, which has to be the same throughout this entire loop. And I also have 3 different resistors. So I have a 10 ohm, well, I have 3 10 ohm resistors, which I can parallel from 10, 10, and 10. And if you parallel 2 of these, it becomes 5 ohms. And if you parallel all 3, it goes to become like 3.3 ohms. So why is this important? Because I have 2 meters in this Kelvin setup, stray resistance that would normally lead to inaccuracies doesn't matter. I don't really care what my resistance is of this whole loop because I'm going to measure current and voltage so I can back calculate what the effective RL is. And what that would really just look like is our voltage from the meter all over the current equals R effective. Now, how do we figure out how much RI is? Again, simple. It's essentially a voltage divider. We first measure the voltage when there's no load. So we take voltage open load. We divide that by our I that we measured there. Then we measure R effective, and that's going to equal R internal. So trivial to do that in Excel with just these 2 measurements, 3 really. Check the voltage here before you connect the load, and then measure these 2. And I will now walk you through that setup. Now to actually take a look at using this setup. So I have my 2 battery terminals here, again with the Kelvin style connections. So we have our voltmeter. This is connected to the load. So here's our load of 3 resistors. Currently 2 of them are hooked up. This 3rd one is just floating here. So when I touch this, it makes the connection. Hooking our battery up. Easy as putting those on there. We can now see we have an open voltage of 8.2 volts. And I do find the easiest way to take this measurement is actually just to quickly do it and use a smartphone and take a picture of the 2 multimeters at the same time versus trying to write stuff down while you're under load. As that battery's heating up, these numbers are gonna shift a little bit. So it's as simple as, okay, you notice our voltage drops to 7.6 and our current is 1.4 amps. Now, what's making that voltage drop, going back to our diagram here, is we have 8.2 volts here still, but we're only seeing 7.6 here. And the reason is that voltage is being split across this RI internal and this R load, which is our power resistors out here. To get a good measurement of internal resistance and how it's affected by load, you should take it at a couple different loads that are representative of where you might be using that battery. And also, temperature is going to be highly dependent. So your battery should be the temperature you're going to be operating at. And worst case would always be typically your coldest operating point. So for me, the other test I'm doing is I've put these batteries in the freezer overnight, and then I've pulled them out and as quickly as possible run through the 3 different loads to collect the data. And that sums up the laboratory portion. Now let's take a look at the actual results from testing some Canon and off-RAM batteries. So looking at the results of this set of testing, I did a few different sets. This is the most accurate. And what I was testing here is a approximately 2-year-old Canon NH type battery, as well as a brand new CarStar P-type battery. Essentially, Canon just in the last couple months, September 2024, released a new battery format that's supposed to be, quote, more powerful. And I was hoping one of the things it did was lower the internal resistance, especially in cold temperatures, so high power cameras could perform better in the cold, or in my case, don't lock up. Unfortunately, at least for the third-party car start battery, that's not really the case. You can look at the graphs on the side. At room temperature, it performs a little better than the Canon, but considering the Canon is a year old, that's not a surprise. They're probably nominally equivalent when they're brand new. And performing at low temperatures, they both perform very similar, which is a 4 to 5x worse internal resistance. And as they're approaching that 1 ohm mark, that camera is going to struggle at full load to get the power it needs for intensive tasks like autofocus and image stability on a large lens, along with actively writing out, recording, shutter, all that good stuff. So looking at the chart on the left here, there's two other batteries. There's an older Canon N-type that's listed that I just wanted to see how it performed. I didn't bother charting it. It performs poorly in the cold, big surprise. And there's also, I retested the K-Star battery as it was warming up, so I'm guessing it was about 40 Fahrenheit. I don't know exactly how warm it was. And it gave, as would be expected, an internal resistance in the middle. One item worth noting is how there's the downward trend of the internal resistance, that as the load, as more current gets pulled out of that battery, it appears to have a lower internal resistance. I think there's two things that explain that. One, I did the lowest current to highest current testing in that order. So the battery was warming up due to the environment. And on top of that, internally, that resistance converts that battery energy into heat. So as I was doing this testing, it's also internally heating up the battery. I think if you perform these in a temperature-controlled environment and you waited a long period of time between each test, you would find that the 10, 5, and 3.3 ohm tests are all closer to 1 ohm instead of them trailing down to 800 milliohm as the testing went on. And that 40-degree Fahrenheit test really shows that, considering the 5 and 10 ohm loads actually included identical data. So anyways, take this data as you will. It's interesting. Unfortunately, my high expectations weren't quite met for the third-party battery. I'd be curious to see how the Canon version works out, if it follows this same trend or if it is significantly lower. If it is, I would seriously consider investing in the Canon battery over this third party. Well, hopefully you guys found this interesting, learned some things about Canon batteries and how to test batteries, and we'll catch you guys later.